Hello, everyone. Thank you very much for joining today for the AIAA Los Angeles section town hall meeting. We have a wonderful speaker and a very hot topic today. But first of all, Happy New Year, everybody. This is actually the official public events. The first one this New Year. Although we actually had the Aero alumni meeting last month and a couple of outreaches to the local high school, including Ms. Nancy's camps, very distinguished high school. Before we started, get our section chair Luis to introduce. I just say something about the logistics. So the people here in person, the restroom is outside the door of this meeting room, but you have to wave hands to the librarian so they can unlock the door for you. So you can see nice, you have a beautiful patio lawn, that's very exciting. Nobody will prepare some refreshment, but because the library charge for cleaning, so we kind of didn't do it this time. But after the event, if you're interested, you can join us with a speaker. We can go to the Corner Burger across street, just 30-second walk to continue the conversation, to know each other better. The library, we have the meeting room until 2 p.m., so we have plenty of time. But we can also move over there. And if you want to grab some coffee, snack, you're welcome to walk there. But I'm pretty sure you don't want to leave during the presentation for doing an interesting talk. And the other thing is about this membership. So if you are a member, highly welcome, is highly appreciated. Remember to renew. If you're not yet a member, please consider join our great family of AIAA, like our speaker and Luis and many people here, and Nancy, Dr. Bradley here. The other thing I want to say is that actually this space sustainability is a very hot topic right now. And actually next Saturday, February 8th, we'll have a mini conference on that. We have 3 more speakers. They'll be more from the industry part. They are going to continue conversation in Lomita Library. Please join us. After today, of course, please enjoy today's wonderful presentation as well. And we have another major event coming up is the, Luis can tell you more, is February 21st, Friday, here in Longdale Library. We are going to have the annual Los Angeles section AIAA University branches mini conference right here. And the CEO, a new CEO of AIAA, Mr. Clay Maury, is going to join us. Of course, right now it's only we are trying to collect the participation from the student branches, so it's not open to the public yet. But please email me or Luis to show interest. We'll add you to a waiting list. So after the student the list has been compiled, then we can add you in. You can also join online. There's also online. It's open for registration for online already, so you can do that. And there's a happy hour. Luis is going to do it next to SpaceX after the mini conference. And in the middle, we have to actually have another event in USC, but the detail has not been announced yet. It's February 18th. As you know, USC, in addition to our speaker today, he got the ESA award. The USC Student Branch Rocket Propulsion Laboratory, they just broke the world record for amateur rocket altitude record last year in October. So there was going to be a recognition event. And also, by the way, this year is the 20th anniversary of the USC Rocket Propulsion Laboratory, as well as the astronautical department. It's a great occasion, so we'll announce it, so you can sign up, join us. So let's welcome our section chair, Mr. Luis Cueva. He will take over from here. Thank you so much, Luis. Thank you.
Thank you, Ken. Quick shout out to you. Thank you for setting this up and organizing it. Really appreciate the work you put into this and the exciting topic we have to listen to today. So Jose, I'm just gonna introduce you real quick and mention the topic of the presentation at hand. So ladies and gentlemen, it is my pleasure to introduce an outstanding researcher in the field of astronautical engineering, Jose Ferreira. Jose is a PhD candidate at USC's Viterbi School of Engineering, where he studies the environmental impacts of spacecraft demise in the atmosphere. As both a NASA finalist, which stands for the Future Investigators in NASA Earth and Space Science Technology, and a Fulbright Fellow, which is an international scholars program, research program. His work is shaping the future of sustainable space operations. With extensive experience in aerospace engineering, Jose has served as a lead systems engineer for an Earth observation small satellite and has contributed to aerodynamics research at NASA Ames and Delft. He has also shared his expertise as a university lecturer in aeronautics. Beyond research, though, Jose has played an active role in global space policy, serving as a delegate of the 57th and 58th scientific and technical subcommittees of the UN, COPUOS. I'm not sure what the acronym stands for. His contributions to sustainability in space were recognized by the European Space Agency when he won the Space for Sustainability Award in 2023. And he is currently the managing editor for the 2024 special issue of the Journal of Space Safety Engineering. He's also a distinguished honoree of the Forbes 30 Under 30 Portugal for 2024. His work has garnered international recognition as it's been featured in the New York Times, Scientific American, CBC Radio Canada, RTP Portugal, and I believe it's pronounced Deutschlandfunk Radio. So please, everyone, join me in welcoming Jose Ferreira.
Thank you, Luis. Thank you for the kind words. Good morning, everybody. Thank you for making the time to join. Good morning, everyone online. It's a pleasure to be here. Thank you for the opportunity to share some of the insights of my research so far, and also basically to share the word about environmental impacts and whether we should care about it and what are the unknowns mostly as of now. I will start with a little bit more about Jose. What is my background? As you mentioned correctly, I'm an aeronautics guy. So I started with my passion for aircraft. I started in Lisbon in Portugal. I did my fair stint in TU Delft, where I was passionate about aeroelasticity, this phenomenon of fluid structure interaction between the wing and the airflow that just exploits, and by exploiting some vibrations. This concept here you see, this flapping wing, was just an idea of harvesting energy to have some sort of a actuated flap to counter gust while in flight. So this is some sort of gust alleviation system. And this was pretty cool. This is what made me fall in love with wind tunnels first. Then eventually that brought me to Ames, to the wind tunnel division. I then pivoted into astronautics when I did my stint as a systems engineer for an Earth observation small satellite, mostly focusing on synthetic aperture radar, but mostly on the designing of the whole system. And something that I usually proudly also mention is that I'm not just my background or experiences. Usually I also mention in my background that I'm a pianist. I went into music school before going to primary school. I started when I was 5, and therefore I also have a conservatory music degree in classical piano. So I could stay a little bit longer here. This is me playing piano. This is me as a footballer playing soccer, which I did for perhaps 20 years. And this is me with my other activities. I'm a very outdoorsy person. I like adventure. I have many lives. I like, as Luis mentioned, the public outreach and informing the general public about what space sustainability is, and not only the major public, but also the decision makers. This is a picture at the Austrian Parliament, but this is the one that I think is the coolest. This is me in microgravity playing a little piano. So blending both worlds. This was a very, very cool once in a lifetime experience. So this is me, folks. Welcome, and I hope this sets the stage for a cool chat. I want it to be informal. I'm going through this set of slides, which hopefully won't be that boring to you, and then we'll have a nice and interesting discussion, just informal, and just ask anything. I'm here to discuss and to also get new ideas. All right. So I really like this image because we may think that this is a meteoroid re-entering the atmosphere, but this is actually the ATV-1, a cargo resupply vehicle to the ISS, re-entering the atmosphere. This may look like a meteoroid. In some ways, it actually does. But there are a couple of differences that are worthwhile noticing. So let's talk about the motivation. Why do we care about the subject of space debris demise in the atmosphere? So the process through which pieces from low Earth orbit mostly come down to the atmosphere, they heat up, they burn up, and they come together as smaller pieces. And the question here is what are the impacts, and whether we can measure it properly as of now, and whether we can say that there are positive or negative impacts from these anthropogenic actions in the atmosphere. I usually like to think that the picture is worth 1,000 words, and this is not really a picture, this is a diagram, but I think it summarizes it pretty clearly. So we are concerned not only with launch events, but also with the re-entry events of upper stages that puts our payload into orbit, but also the actual re-entry of spent satellites, what we call derelicts. And these may become a concern due to the increased launch and re-entry trends within the era of mega-constellations. But we'll look into this a little bit further down the line. So this is what we care about, this satellite end-of-life destructive re-entry. And we believe by learning about satellites, we could also learn a fair amount about launch vehicles re-entry. Although the dynamics is a little bit different, but they follow roughly the same principles. So this is an attempt to reconstruct the re-entry of that vehicle that we just saw first. So this is the cargo resupply vehicle to the ISS that re-entered in late 2008, 2009, if I'm not mistaken. And we see a bunch of cool stuff here. Firstly, we know that there is an explosion at 80 kilometers altitude. Then we have a lot of confusion. We don't know what is what and where every single bit is. And then we see here this attempt of mapping the chemical species to some sort of components within the spacecraft. This was a very good attempt, but this essentially shown that even though we know the ballistic coefficient and all that, this essentially shown that we don't really understand the breakup process of spacecraft upon re-entry. And this motivated the development of modeling efforts to further understand it. Why does this matter? Essentially because we should be sure about whether or not these pieces of hardware re-entering from orbit can hit any of us on the surface. And by understanding this phenomenon, we would be able to predict whether or not we should worry about these large spacecraft hitting someone on the ground. This allowed us to, or essentially the general community, to develop some modeling efforts. This is the results generated using an European Space Agency tool called DRAMA. This is for a Sentinel-1 spacecraft, which is a large one. And essentially, this model, informed by the experiences, the observational experiences in wind tunnel testing, tells us that, well, these are the demise points. So the spacecraft is expected to have the appendages demise at around 90 kilometers altitude, and then it burns up. And then we are only concerned about what gets to the ground. And this is what we try to minimize, at least from the operator standpoint. We want to prove that nothing gets to the ground, which makes total sense. If nothing gets to the ground, we may not need to go for a controlled re-entry. We don't need to aim for the ocean. Essentially, we can just leave the satellite re-enter at some point, if abiding by the 25-year rule, which right now in the US is a little different. We have the 5-year rule. And essentially, this is all from what we care about from an operator perspective. These efforts were also further informed, as I was mentioning, by experimentalism. some wind tunnel testing, which I really want to show you this video because it's super cool. So this is a solar array mechanism in a wind tunnel. You turn on the wind tunnel, or the arc heated wind tunnel, I should be more precise, and this is what it happens. It just burns larger chunks than smaller chunks. And this is what happens. Of course, that this is the chemical composition of this array is varied. We have a lot of aluminum alloys, but we also have other kind of species here. But the truth, I mean, the point here is for the modeling efforts in trying to understand what gets to the ground, this is it. If it burns, if it gets into very small particles, we as operators are fine because it doesn't get to the ground. We don't need to care about the casualty risk. All good. Now, let's look at the launch trends. And this is I would say perhaps the infamous plot where we look at the object count as a function of time. And we see the so-called hockey stick effect, where we have this almost exponential trend in terms of the amount of objects in orbit. I would say that this only tells us part of the story. When we think about the mass that comes down to Earth and comes and is injected in the atmosphere, I usually prefer to look at the mass that actually re-enters. And if you can see, there is, of course, we can think of it as a linear trend, but the trend is not as significant as the number of objects in orbit. Well, this has all to do, of course, with the miniaturization of spacecraft, right? I mean, we are now building smaller spacecraft, so we have more objects, but let's say that the specific mass is lower. So we have more objects, but they are of lower mass, which means that the object mass doesn't follow the same exponential rule that as the object count. This doesn't mean that we don't need to care about it. It just means that we have different lenses to look through the same to the same trend. Now, I would say that the one that is most important to this case are the re-entry trends. So in this plot, which basically just uses empirical data from the Space Debris Office report of the European Space Agency, we can see here the satellites and launch vehicles, upper stages of launch vehicles launch into orbit, and the other bar is essentially the ones that re-entered. And we can see this huge offset between the number of objects that go into orbit and the one that re-enters. We see that only in satellites because, of course, satellites have a given lifetime, so we wouldn't expect that the satellite launched in 2020 would re-enter in the following year. So we would need to wait for it for, of course, the lifetime of the spacecraft for it to re-enter. The same doesn't happen with launch vehicles. If you check these bars, actually you see that there is some sort of balance between the upper stages that are launched and the ones that re-enter. Most likely because these upper stages, once they inject their payload in orbit, they tend to re-entry in a shorter time frame when compared to satellites. Borderline, what I'm trying to convey, the message I'm trying to convey is that this exponential trend that we are seeing here, it will likely hit us up in a couple of years. So we would expect that the amount of re-entries would follow this trend in a couple of years. And this is why we would worry, in principle, about the mass that re-enters in the atmosphere and the chemical composition of these objects that re-enter in the atmosphere. Now, we also may look at some unintended re-entry trends, which of course comes as a consequence of deploying more and more objects in orbit. This is just a very benign example of what happened in February 2022. Unexpected geomagnetic storm, the density of the atmosphere at very low Earth orbit increased, higher drag, 40 Starlink spacecraft demising the atmosphere without much to do about it. This is something that we don't have, we can't do anything about it, but this is just an example of an unintended re-entry, which of course, if we are introducing more objects in orbit, this is more likely to occur, even though this is an event that we cannot predict. We hope we can predict it one day, but to my awareness, to my knowledge, it's very difficult to do so as of now. So what is the problem, right? So as I was mentioning, the re-entry mass is expected to grow, to increase. I'm mentioning here 3 to 4 times in the next couple of decades. I'm not going to argue about numbers. Different entities have different predictions depending on their orbital environment model. I'm not going to argue about that. Those are very well-defined sources that are compared against each other. Essentially, you just pick your poison and just go by those numbers. The point here is that most of the mass is expected to burn up upon re-entry. And this is something that we design our spacecraft for, because this means that nothing will hit the ground. The question here is there an unintended consequence here, which is, well, if it doesn't hit the ground, it's because it stays somewhere. That somewhere is in the atmosphere. So are there any impacts of it? The question about impacts, and I want to make a short timeout break here, is how do we define an impact? The way I would define an impact is changing the status quo. It doesn't need to be positive, negative, or neutral. An impact being a change in what is currently out there. So by acting and changing the natural environment, we are having an impact. Then we can have an objective to classify this impact, to categorize this impact. This can be positive, neutral, or negative. And this is something that hopefully research will tell us. But to my point of view, we can logically say that there is an impact based on the fact that we are changing the environment with these added anthropogenic compounds. These impacts can be not limited to this list. There is a lot of research out there. Some of these impacts can include radiative forcing and global warming. So you can think of these small particles to act as mirrors or reflectors of incoming radiation. And you can think of different scenarios. This can actually block radiation coming from the sun, and this will probably point us to the geoengineering examples where we use particles of aluminum to block incoming sun radiation and therefore cool down the planet. But it can also reflect or absorb radiation because, for example, aluminum oxides have a darker color and therefore it may tend to absorb radiation more. So I've read studies that point different ways, positive and negative radiative forcing. So it will heat up and cool down the planet. This means that we just don't know enough about this. And that's why I've pointed out that impacts can be neutral, positive, or negative. It's very hard to answer that question right now because there are a lot of unknowns. And the same holds true for the other examples. Ice nucleation and cloud condensation, especially at high altitudes. Smaller particles like this that are created concern atmospheric scientists because they may just impact the cloud condensation. It doesn't take much or many particles to impact in this, and then the consequences in the long term are, to my knowledge, not very well understood. Last point in the list, stratospheric ozone concentrations. This was something that was a concern in the late 90s with the emissions from solid rocket boosters from launch vehicles with direct injection at stratospheric altitudes where the stratospheric ozone layer is, not layer, but there is a higher concentration of ozone at that altitude, and that's why we call it a layer. And the same principles can be thought for this re-entry, but in this case, these particles will come from above, and this is the concern about stratospheric ozone concentrations. Now, who cares about this, right? We may be wondering that this is a clear, well-posed scientific question, but who cares about this? Not only, of course, the general public, but also regulators. So the FCC had acknowledged this potential effect on Earth's atmosphere from spacecraft launch and re-entry in 2021, and it actually acted upon it in 2022 by saying that SpaceX would only be given a preliminary approval to launch their Gen 2 Starlink if they were committed to explore methods to collect data on formation of aluminum from satellite re-entry. And this is, of course, on the national side. On the international side, we have policies from the IADC guidelines, which is this committee of aerospace agencies from around the globe that addresses environmental concerns, mostly related to space sustainability. And last but not least, the United Nations, which had repeatedly pointed to this subject. So now that I spent a fair amount of time in the motivation, I hope you guys are all not motivated for to check what can be done, what has already been done. That's why I'm going now for measurements with this cool image of with an actual measurement campaign being carried out. And after we go through this section, let's see what we can do. How can we approach this subject from another perspective? So far, what we have done is collect data at a distance. So with these airborne remote sensing campaigns, we essentially fly an aircraft at the highest we can, in this case at 20 kilometers altitude. We look up and we try to get the spectrum, which would tell us the chemical composition of the spacecraft. This may sound a little strange to us because if we build the spacecraft, we know what's inside. So why do we care about what's the chemical composition of what re-enters? Well, it turns out that we know what's inside, but we don't know how it reacts during this high temperature, high enthalpy reaction with the surrounding environment. And therefore, even though we see pretty clear elements of the structure, for example, aluminum is 90% of aluminum alloys, and you also see other constituents of aluminum alloys, such as titanium and magnesium and so forth. We also see the results of the reaction with the atmosphere. So we see here nodes of aluminum oxides. And this is exactly what we want to measure. So we know what's inside, but we don't know how it behaves when it reacts with the atmosphere. And this is the question mark that we need to address. So we are now on the microphysics and chemistry side, which is actually the question mark. We don't know what happens. We just know that this kind of chemical species are created, but we don't know the size of these particles. And this would actually help us understanding what are the environmental impacts, or whether they are positive or negative in the future. So that case was the ATV-1 re-entry in 2008, 2009. This is the Cygnus OA6 re-entry. Those are both cargo resupply vehicles to the ISS. The second re-entry at the airborne remote sensing campaign, very similar to the first one. We see once again aluminum oxide, not a surprise. Again, spacecraft structures, the chassis of the spacecraft is made out of aluminum alloys, so here it is. The most recent attempt on this was in September 2024. This mission from the European Space Agency Cluster 2, also called as SALSA, had a controlled re-entry path over the Pacific Ocean at 80 kilometers altitude. The private jet flew again at the same altitude. And the reason why I'm showing you this, even though there are no public results yet, is because I just wanted to show you how these measurements are done. And as you can see, this is as simple as having a couple of cameras pointing out the window, trying to get where this hot ball is, pointing the camera up there, and then just trying to get some data from it. This is as simple and as complicated as this. We can also try to do it in another manner, meaning not doing airborne remote sensing, but in situ data collection. So collecting data at the altitude we're flying, which means that at that point, we are hoping to gather data of these particles after they have settled down to the altitude of 20 kilometers. This study is probably one of the most important in the last couple of decades. And essentially, this initiative from NOAA, they flew a WB-57 in Alaska, so in the poles, and they were able to spot again. They were able to spot again aluminum and aluminum oxides, which are not surprising because, again, there are also these chemical species in meteoroids, for example, which is usually a counter we hear. I mean, these chemical species we see, they are also present in meteoroids in a smaller amount, but aluminum could also be a source for this. The interesting part is that there are other species that are not naturally occurring in the atmosphere that were spotted, such as niobium, hafnium, molybdenum. And this is what made these researchers conclude about that this can only be, the source for this can only be anthropogenic, can only be human-made. And they were also able to estimate that up to 10% of the aerosols at that altitude already contain some degree of these particles. What's the concentration? They weren't able to tell us right away because, of course, they resort to a very small sampling size. But these are the conclusions, and the conclusions are at least eye-opening, and they resonate. They in some way they turn on an alarm bell so that we can further understand what's going on. This is not new. Once again, this was done in the late 90s. A very similar method, I would say. Of course, technology had evolved since then. But with the exhaust plume of the solid rocket motors from the Titan IV and also from the shuttle during the shuttle era, this study analyzed 3 launches, Titan IV and 83 and 85th missions of the space shuttle, and they were able to retrieve the concentration and the particle size, which is the most important part here, to actually then model the environmental impacts. The conclusion about them on the modeling side was that this small ozone hole that was punching the atmosphere while the rockets were launched would close in a week time frame after the launch. But the most important part is that the enabling factor to measure those impacts is actually to gather this particle size distribution, which ended up to be trimodal. So we see 3 peaks and so forth. I'm not going to dive into many details about it, but this is what I would think that it's the enabler for us to understand the microphysics of the problem. So with this, I would just make a small break here and ask ourselves, why is this so difficult to measure? Because as we saw here, I mean, we were able to do this for the launch vehicles, but for the objects re-entering at high altitude, we essentially cannot get there to measure the particle size on the place. And if we wait for it to settle down, we essentially do not fully understand what happens in the way down from the mesosphere to the stratosphere. And the reason why I'm showing this is basically we are limited in terms of observations to this altitude, 20 kilometers altitude. We can't fly much higher than that. We can go a little bit above with high altitude balloons, perhaps until 40 or 50 kilometers, but above that they will just burst. The only thing that can actually measure through the mesosphere would also be a sounding rocket or a regular rocket, but then we would be very lucky to get a re-entry to happen at that same location. And for those of you that have worked a little bit with re-entry, the uncertainties connected or associated with re-entry are just huge. We are lucky to be able to narrow down the impact on the ground to a huge area in the South Pacific Ocean. So nailing down what it happens in the sky, at what altitude, at what instant in time, is almost it's almost unheard of. So this is the challenge. And then if we let it settle down to an altitude where we can measure, then we end up with a byproduct of those small particles. So these particles will settle, they will probably grow in size, and then we will see the result of that growth. And usually they tend to circulate towards the poles, and that's why those measurements from NOAA were carried out in the poles. But essentially, we only see the end of the story if we do this measurement at 20 kilometers altitude. So the question here is, how do we actually understand the beginning of the story at 80, 85 kilometers altitude in the high mesosphere? Because that will also inform us about what could be the environmental impacts in the end. All right, are you still all with me? Okay, so let's now go a little bit into
on that last graph, the curve, the yellow curve. What was it showing you?
Oh, temperature and density.
Repeat it.
Oh yes, repeating the question. So this yellow curve tells us the air temperature as a function of altitude, and the gray curve shows us the density of air as a function of altitude. It varies as a function also of the solar minutes of the solar activity. So when the sun is in the peak of solar activity, we tend to have a higher higher density and higher temperature to the air, and the other way around. This solar cycle usually ranges from 9 to 11 years, which means that we need to account for that. But this is just purely informative. I think the point I was trying to make here is showing how inaccessible it is to measure at these altitudes, closer to 100 kilometers, and therefore the limitation on understanding the microphysics and chemistry of this phenomenon. My pleasure.
I sort of
Yeah.
follow-up question. So the problem with using sounding rockets is that it's hard to get a sounding rocket launch in the right location following a re-entry, right?
Yes.
Maybe we should talk about that later.
Okay. Yeah. Comment here being the difficulty of measuring in situ with a sounding rocket is being able to sync up the launch location and time with the re-entry event. This was basically a comment for food for thought, I would say. All right. Now I'm going to share with you the way I've been approaching it during my path as a researcher at USC. So given the limitations of measuring this in situ, what us usually do, humans, is we try to resort to computation models and try to model this to the best of our capabilities. This is not new. We have done this with aircraft, and we have also done this with re-entry at some extent, but not really at the microscopic level, as I'm going to show you. This has a very pompous name, molecular dynamics simulation, but essentially we're just simulating atoms colliding with each other and see what happens, and then try to extrapolate reactions or relationships from microscale to full scale, and hopefully that will tell us what's going on. So the way we do it, and this is now going to be a little more cumbersome in the sense that we are going to see some Greek letters, but I promise this is only going to be 5 minutes. So we first have a re-entry from low Earth orbit, LEO. Then and at that point we have this molar ratio, so this ratio between oxygen and aluminum that we care about. Let me make a stop here to explain a couple of things. So air is a mixture that has different chemical species involved. The most prevailing is nitrogen, but usually nitrogen is not very reactive with metallic species. And then the second most prevailing is oxygen. Then why are we referring to aluminum? As I was mentioning earlier, aluminum shows up in all spectroscopy from re-entries. We know from past observations that it can be used as a geoengineering tool, as I was mentioning before. So people had already looked at aluminum as a source for geoengineering, and also because it was one of the species that concerned scientists the most during the solid rocket motors investigations in the late 90s. And most of all, it's because it's the most prevailing chemical species in satellite structures and in spacecraft structures. So it makes all sense to look at the reaction of oxygen and aluminum to start with. So firstly, we understand what's the molar ratio, meaning how much oxygen there is in comparison with the amount of aluminum. We try to keep that ratio in the molecular scale, in the micro scale. And then we take from this simulation, we take the atomic mass for every single cluster of particles, and then we extrapolate the diameter of these clusters of particles, and then we try to get some statistics out of these distributions. So we use something called reactive molecular dynamics simulations. I think the only thing to get from here is that we compute the oxygen and aluminum interaction at each time step. So essentially, we have this interatomic potential, which is this attraction repulsion relation of forces, wherein when we have an aluminum atom getting closer to an oxygen atom, it usually repulses, and there is at some point that it reaches a stable point. Then if we get them too far away from each other, there is basically no force attracting or setting them apart. So we use this, and of course that we also set the velocity of oxygen to impinge in this aluminum structure. And essentially this represents covalent and non-covalent bonds if you are into chemistry. And the end result is, as I was mentioning, is to get the mass and the diameter of these particles. I would say that this, no, before we get to an actual image, this is the approach. So we have a generic small satellite from a mega-constellation with these dimensions, this mass, with an aluminum mass fraction of 30%. And essentially re-entry conditions from low Earth orbit at 7.8 kilometers per second. And then we essentially do this. And I think this is what you were waiting for. This is a visual clue of what is going on. So as you can imagine this as we are scooping a little bit of the surface of the satellite, and we have this column of oxygen that is impinging into the structure. What happens is, firstly, we have melting of the aluminum structure. We have the oxygen impinging at the velocity to impinging the structure during re-entry. And then we have these clusters of particles, essentially of aluminum and oxygen particles, and then we study it. We take the properties out of it, and we try to make some sense out of it. Some formalisms. Essentially, the simulation, the domain of this simulation is very small in the nanometer scale, from 0.1 to 10 nanometers. We have here some properties of the aluminum substrate that, unless you're very interested on it, I'm going to skip it. And essentially, we heat up the temperature. The surface temperature will go up to 2200 Kelvin, as I was mentioning earlier. And then, once the reactions are finalized, we analyze the properties of these byproducts. So this is how it looks like. So we have firstly the oxygen molecules impacting into the surface. There is going to be some dissociation of molecular oxygen into atomic, and then we see the chemical reaction of oxidation, and this is the end result. A couple of details here. We do this in an incremental way in the terms of number of atoms. So we test an increasingly larger number of atoms with an increasingly larger domain, so that we can pick up some trends with regards to the domain. So we would ask yourselves, okay, is the particle size increasing because the domain size is increasing? This is what we want to test our hypothesis again by computing the particle size distribution. Yes.
So I'm going to show my ignorance of chemistry here, but I would be expecting to see Al2O3 because of my terrestrial understanding.
The question is about Al2O3. Would be expecting to see Al2O3. Al2O3, stoichiometrically, that's correct. Point with Al2O3, and the reason why I always point to ALO instead of Al2O3 is that we are looking at substances in the verge of solid to liquid state. Al2O3 would be in the gaseous state if we only have a molecule of Al2O3. So what we see here are particles that are on the verge of solid to liquid state because the melting point of aluminum oxide is very high. And this is why we see this configuration. So it's a cluster of aluminum oxygen. And then we are going to see that something called the coordination number is that a single atom of aluminum will connect with several atoms of oxygen. The reason why formally I'm not referring to this as Al2O3, it's because it's not in gaseous state. So it's just a detail. But your sense is correct. Stoichiometrically, when we refer to the reaction of oxidation, we refer to Al2O3.
Thank you.
So this is essentially what we use this simulation for. So we run the simulation, we do some post-processing, we take the mass of each cluster, essentially, because we know the mass of aluminum and we know the mass of oxygen. Then essentially by knowing their density as well, we can take the diameter because we will then know the volume. So it's essentially just a definition of density, mass over volume. Then we are able to compute something we call the aerodynamic diameter. And we are able to assess a couple of interesting things. First one being, there are a couple of aluminum clusters that are of smaller size. This essentially just are the consequence of the kinetic impact, this momentum transfer between the incoming oxygen and the aluminum atoms that are in steady state. Then we also see that the larger clusters are made out of aluminum oxides, and this is due to the fact that there is this impingement of oxygen, and then they react together and they grow in size. Something that I didn't really emphasize earlier when I mentioned the molar ratio is that the molar ratio is 0.13, meaning that there is more aluminum than oxygen during that 90-second window of very high temperature for reentry. This in some ways tells us that there is not enough oxygen to fully oxidize the aluminum content. I'm saying that, and by my point, please take my point that this is only during the primary ablation event. I'm not saying anything about what happens next. Most likely, these particles will get oxidized in the surface, most likely. But the full oxidation reaction, where we have particles dissociation or chemical species dissociation associating with each other, this is something that oxygen concentration is not enough to provide. So that's why we see still a couple of aluminum clusters remaining on the lower sides of the spectrum, so the smaller particles. And then we see here this large cluster, which, I mean, I had to call it aluminum oxide cluster because there are a couple of oxygen atoms there, but this is essentially all aluminum. So this is a huge chunk of aluminum that survives re-entry. Please note that this is cluster count, not cluster mass. So we would expect that if we were going to a mass count, this shape would be much different. But the point here is this follows a log normal distribution, which we're happy to see because that was exactly what was the output from the previous research in the late 90s. Then we do a couple of analyses, and this is the coordination number that I was referring to before. Essentially, we check to how many atoms species A is connected to. And this essentially allows us to conclude what's the fraction of aluminum that gets oxidized during this primary stage. The conclusion we get to is that the oxidation yield is around 32%, which means that 32% of the initial aluminum is oxidized, the remaining is not. So this is a ballpark figure, of course, and this is, as all numerical approaches, this is just an estimation. But I think the point here being, we always thought that all the aluminum is going to be oxidized. Everything is going to be oxidized upon reentry during that high temperature stage. And this shows us that perhaps that's not really the case and that we need to look further down into that. These may have several consequences, especially into atmospheric models, because we have always thought that essentially the all content of aluminum is going to be aluminum oxide, and that's our starting point in atmospheric models. These may show otherwise, and that's why this may bring a different perspective to the problem. This is just an interesting assessment or analysis of what's going on. Essentially, the full lines are for case A through case D. Let's recall that case A through case D is an increasing number of atoms, but I have normalized it. And it tells us the number of bonds. So we see here that the number of aluminum oxygen bonds in the beginning is 0 because the oxygen hasn't hit the aluminum structure yet. Then we see an increase, a huge spike, and then we see that they converge to the same fraction, to the same number. Here we see at the dashed line, we see the number of oxygen-oxygen bonds. So recall that we start with molecular oxygen, and then they progressively get dissociated, and they are essentially consumed, fully consumed. And this is the point that tells us that, yeah, we consumed all the oxygen, and if there were to be more oxygen to oxidize the aluminum, we probably would end up with a higher aluminum-oxygen bond count. This is, again, just a function of stoichiometry. If I were to run this simulation at a lower altitude, not at 85 kilometers, but at 70, of course, that the density of the number of oxygen atoms would increase, and then these results could be different in that sense. But that's something that we are currently working on, so that we have different altitudes as an input for this particle size distribution. And then this is essentially it. So we then compute the statistics of this particle size distribution for all the cases we compute. And then we extrapolate here mu x meaning mean of the distribution and capital M meaning mode of the distribution. For those of you that are statistics savvy. And then we essentially compute the macro scale. So this is the point at which we go from atomic scale to macro scale statistics of the distribution. And then we get to the conclusion that our estimation points to a mean of 4.1 nanometers for these smaller particles and the mode of 4 nanometers. So how does this compare with what was measured so far? So let's recall that this PALMS experiment, the one from NOAA, took place at 20 kilometers altitude, and it had the detectability threshold of 100 nanometers. So they couldn't really get anything below that number. Let's also recall that these particles are aerosols, so we can think of it as these clusters dissolved into a solvent. So it's a drop of a liquid with particulate matter inside. And essentially the point I'm trying to make here is that these particles that are generated up high in the mesosphere are uncoated, whereas the ones that were measured are coated. And something that we know about the stratosphere, not the mesosphere, is that these smaller particles tend to come together. This is called the coagulation mode for these smaller particles. So these smaller particles, when in close proximity, they tend to coagulate and grow in size. Point is, we don't really know much about how this works in the mesosphere. We know a fair amount about the stratosphere because we can actually gather data with high altitude balloons and so forth. But above 40, 50 kilometers, our atmospheric models are essentially just extrapolations of what we know until that altitude. So this is one of the big question marks: is how do these particles behave after they are formed? How fast do they grow? These will determine how fast they would settle in the atmosphere and where they will end up after being brought, most likely to the poles using the global circulation. Now let's take a step back and look at re-entry fluxes. So we looked into the microphysics and actually the huge question mark in terms of how all this works. But then now let's take a step back and look at the beginning of the problem in terms of what re-enters in the atmosphere and what can we actually say about that using these very, very preliminary results about how these particles behave in the atmosphere. This is actually, pretty honestly, high school math. This is just basically if we use the chemical species from a given category, either satellites or launch vehicles, S or LV, or micrometeoroids, because this is the point at which now we are going to compare the anthropogenic sources, the human-made sources, against natural sources. So this is something that it's a very, very fair argument is, oh, but micrometeoroids are part of what made our atmosphere look like it is today. I mean, there is a constant bombardment of micrometeoroids to the atmosphere, and that actually contributed to the chemical composition of our atmosphere. So in other words, there had always been aluminum being injected in the atmosphere because there is a mass fraction of 1.2% in micrometeoroids. So how does that compare with the anthropogenic injections? This is actually a very straightforward question to answer. We take on that initial plot that I showed you about the mass that re-enters. We multiply it by the mass fraction of aluminum and by what's the demisability, or how much of that mass fraction is injected in the atmosphere versus what gets to the ground. And then we can also take that mass and use the oxidation yield that we computed from our molecular dynamics simulation and get an estimation of how much aluminum oxide was generated at the higher atmosphere. I'm not claiming anything about what are going to be the impacts. This is just a pure flux analysis. And so here we are. So these are all pretty well-established sources. We take micrometeoroids with a mass fraction of 1.2%.
with the demisability of 100%, meaning that everything burns up in the atmosphere, everything stays there. And then we do the same for satellites and launch vehicles with different demisabilities. This is based out of a couple of sources and also a couple of past experiences. And then we get to this, which is the aluminum mesospheric influx when comparing the influx of micrometeoroids against human-made sources. Of course, that the meteoroid flux is constant, or I'm assuming it constant. Of course, that depending on what source you look into, you'll get different numbers, but we assume that it's fairly constant for the sake of the argument. And then we essentially compare it with launch vehicles and satellites. And the very interesting thing that people usually are not expecting is that the contribution as of now, at least with this simplistic approach in terms of aluminum, comes mostly from launch vehicles. And that comes once again because we haven't been hit yet by these hockey stick effect that we are expecting to hit us. And this is where our concern comes from. It's not really because of what is happening now, or it may actually be, but I think my point is it will get worse. That's what we should at least look into to get ready for it. And essentially, I mean, this is worth for what it's worth. I mean, we have this increase here of 39% per year on satellites, mass aluminum contribution from satellites, whereas from launch vehicles, there is an increase in this percentage, but it's not as significant as in satellites, which is pretty much expectable. And then just to make some sort of back of the envelope calculations in terms of long-term accumulation. And this was actually something that I wanted to emphasize, is that the excess ratio between of anthropogenic objects versus micrometeoroids when it comes to aluminum is, as of last year, of 86%. What I'm saying is that we are almost doubling the amount of aluminum in the atmosphere as of last year. I'm pretty sure that you could find other sources that are more concerning than mine. I'm being very, very, very conservative in this approach, and this already shows a 2x factor, or close to 2x factor. We cannot say right away that this is going to be negative, positive, or neutral. My point is that there is an impact because we are changing the status quo, and that it's important to look at it. And then, of course, if we look at future worst case scenarios, then it's again the point that I was mentioning earlier: pick your poison. You look to whatever orbital debris model you extrapolate into the future, and then you may come to very daunting figures. Speaking about last year, my estimation is that we had at least 50 metric tons of aluminum oxides injected into the upper mesosphere, so up high. I don't claim anything about what came down, where it came down, where it ends up, how big these particles are. I'm just focusing on what happens here, and then we have a huge question mark about how fast these particles come down. So I think we are reaching a good point to start our collective brainstorm and discussion. Just concluding with some remarks. I believe the takeaways here are that, contrary to what was previously expected, this model shows that solely a fraction of aluminum is oxidized during the primary ablation, which counters what was some sort of the common belief until this study was published. The size of these byproducts follows a log normal distribution, which was nice to see because it kind of makes sense when compared with previous research, showing some similitude mostly with the solid rocket motors from the 90s. Now, why is it important? And I think this is the best takeaway, or what I want to focus our discussion on is, well, firstly, it was thought that these small particles were not created during spacecraft ablation. We thought it was mostly microparticles, but we really didn't think. But we also didn't have much evidence otherwise but we didn't think that nanoparticles were generated. And this can, of course, influence the list of impact that I mentioned earlier, because this is an input to atmospheric models, and then this will hopefully tell us what is the impact. I think something that we should also keep in mind, and that's the science effort on this point, is that mesospheric microphysics is it's mostly unstudied. And I would also add the chemistry is mostly unstudied, not because there is lack of will, but because it's very, very hard. So there is definitely a need to further understand what's going on at these altitudes, essentially from 50 to 80, 90 kilometers. And the other point is atmospheric models are as accurate as the data we have to validate them, meaning that if we don't have data from 50 to 80 or 90 kilometers, it's very difficult to claim or to make very concrete and solid statements about whether these impacts are positive, negative, or neutral. Clearly, the evidences point to a concerning input value, but the point being that we don't know enough about what happens at those high altitudes. So I get back to my initial question, which is, what are the environmental impacts of this phenomena in the atmosphere? And clearly we can list down what the impacts can be, but to my point being that to further being able to classify, to adjectivize those impacts, we need to learn more about the microphysics of the chemistry in the mesosphere. So finishing up with some bedtime readings for you guys. This is essentially the compendium of what I've been publishing over the years about this subject. I hope it doesn't give you much insomnia. If so, please feel free to complain to me. And yeah, let's get to the discussion. Thank you very much for your attention, and happy to open the floor for questions.
It's fantastic that the atmosphere being as large as it is. It seems fantastic, the atmosphere being as large as it is in diameter at that altitude, that the launch vehicles would have such an impact of doubling the aluminum in that area. Is that what am I missing?
Yeah, so this is the drop in the ocean argument, right? Which is totally fair. I would say that the point here being that the natural contributions to the amount of aluminum, even though there are so many, that the mass of micrometeoroids re-entering the atmosphere is so large, there is only a very small fraction of aluminum in that mass. And I'm not even addressing the points of differential ablation, which makes me wonder whether that 1.2% of the aluminum mass in micrometeoroids actually ends up in aluminum oxide form. That's just another side note. I'm just giving it that all that 1.2% of that mass will end up in aluminum oxide, or will end up being injected in the atmosphere. Point being, even though there is this flux of aluminum in the atmosphere from natural sources, which are micrometeoroids, the mass fraction in launch vehicles and in satellites is considerably higher. And that's what makes the 2x figure, or the multiplying, or we're already injecting as much aluminum as micrometeoroids do. Now, question, and I think your point is whether that's enough for us to concern about, whether this is going to be to have any sort of negative impact. The very straightforward question, the answer that I'll give you is we don't know, and I would be surprised if anyone would be able to claim directly that they know. Point is, we are doubling that factor as of last year, and with the increased re-entry predictions, we are going to go much further than just doubling. And that's the question mark, whether the atmosphere will be able to take that and not react negatively to that. It may also turn out that there is a positive impact, that we are blocking sun radiation and helping out with with global warming. That's, I think, part of the scientific mindset is to be open to, and of course we need to consider all perspectives, and that's what we do. My point here is that we need to get the physics correct before we jump into conclusions about positive or negative impacts.
You would have a follow-up?
Has anyone looked at the thermal model of what would happen if there was a shell of absorptive material there between the Earth, the shell, and then space?
Can I ask you to clarify your, in terms of a shell of, yeah.
Let me answer this first, and I think there is something online, but let me answer this first. What you're referring to is this concept of geoengineering, where we would inject this, no?
Your shell.
No. If the aluminum oxide is forming that barrier, the sun hitting it or Earth hitting it, has anyone just done that model?
Yeah. Okay. Yeah. So the answer to that question is there have been some studies done on that sense, not from the geoengineering perspective, but from the contribution of actually anthropogenic objects from space, be it satellites or upper stages of launch vehicles. And that's what I mentioned in the beginning, that I've seen different conclusions towards negative or positive radiative forcing. And I think the point here being that there are too many unknowns at this high altitude. And the coagulation rates, for example, how these particles come together, and the assumptions that those endeavors took may not really completely align with nanoparticles that are generated here. And this just shows us that there are a lot of open points, a lot of unknowns, and atmospheric models are only as good as the data we have. So that's why I was mentioning in the end that to further claim for positive or negative environmental impacts, we first need to further understand the microphysics at high altitudes. But yeah, to answer your question, yes, there are studies. Some studies have been done and carried out. It's just a matter of how they are definitely accurate with respect to what's available right now. The question being whether what's available right now is the atmospheric models represents. It definitely represents our knowledge, but whether our knowledge is accurate with respect to reality at those high altitudes. That is basically my point.
Hey,
please go ahead online.
Yeah, Jose. Before we get to the raised hand here, there's a couple questions in the Q&A section too, to be precise. The first one is from AC, it was sent at 11:55. During the re-entry, I assume the temperatures are high enough to form a plasma, which also heats the atmosphere surrounding the solid materials. So are the atmospheric gases heated to temperatures sufficient to form any nitric oxides? As a follow-up, if the nitric oxide species are generated, are they significantly contributing to ozone destruction?
That's a very good question. There has been, it's a very well-known concern, the N2 dissociation during atmospheric re-entry and the possible recombination with oxygen. It's actually been used as an argument against supersonic flight, given that it may indeed create nitrous oxides, which are very well-known global warming potentiators, if we could say in that way. There is a very good study by Connor Barker from UCL, University College of London, that considers that as a potential source for global warming impacts, which I would definitely recommend reading. So the answer to the question is yes. How could it influence the amount of oxygen I'm considering in my simulation? That would be a different question. It depends on a lot of variables, especially flight path angle during reentry, reentry speed, and so forth. We know that nitrogen dissociation happens at higher speeds than oxygen dissociation, which may bring the question of what's the attitude and what's the actual state vector of the satellite upon reentry. So that's definitely something that we are overlooking in this simulation by not considering nitrogen in tandem with oxygen and aluminum. The reason for that comes from a limitation in the model, which refers to it's very difficult to have an interatomic potential that includes nitrogen, aluminum, and oxygen. So we choose here to start with oxygen and aluminum to show how this model could be applied to measure this phenomenon. And to my awareness, I don't think there is an interatomic potential available to be used, including nitrogen and aluminum and oxygen. In case there is, we would be happy to run a simulation in that sense. But the reaction, the impact in the creation of aluminum oxide would be just because nitrogen would consume oxygen that would otherwise be used to oxidize aluminum. So this would be my comment. But you have a very good point, and it's something that has been looked into, the contribution of NOx created during reentry, to the shockwave and the plasma associated.
Great. The second one here is from Ken McLeod, and I'm not sure if this is more of a question, but maybe a comment. Let's see. In the summary, takeaway 3, the human contributions are actually equal to the micrometeoroids, sorry, not double. Needs a clearer wording. I don't know if we can go back to that slide real quick.
Yes, happy to clarify.
Yep.
Yes. Could you recap the question?
Yeah, like I said, I think it's more of a comment. So in the summary, takeaway 3, the human contributions are actually equal to the micrometeoroids, not double. Maybe.
So this is the questioner. I'm unmuted. When I first read it, it said that the human contributions were double those of the meteoroids, and I think that's not what it really was intended to say. It was intended to say they're equal, and therefore they ultimately do double that total.
Yes. So point being, and thanks for the question, and for happy to clarify. Point being that we have an excess ratio of 86%. So we are almost matching the contribution of micrometeoroids, which makes the total being twice as the initial from natural sources. Does that help clarify?
Yes, I had already figured that out. I just was recommending that you word that a little different way, since it's so easy to interpret it as meaning the human contribution is double that of the micrometeoroids.
Oh, all right. Thanks for the point. Yes.
Yeah, thanks for so much careful work and for showing it to all of us.
Thank you.
John here. Can you hear me?
Hello. Yes, loud and clear.
Yeah. So again, yeah, thank you so much for bringing such light to such an important aspect of the space industry right now and space development. Not enough people are talking about it, and really very detailed. So I do appreciate this on such an important aspect. And as it relates to space debris, which seems to be on everybody's mind at this point. And I just like to comment that with the fact that obviously we can go ahead and need a lot more studying on what's going on at these sublimation and plasma events in the stratosphere, and then raining down, so the effects are obviously negative to potentially on harming life and limb below for objects that do not sublimate or disappear, as some people call it, in the atmosphere. That could happen and probably will, as well as the environmental impacts are going to show to be very detrimental to the atmosphere in the future. That the only real answer is to keep everything in space. As I say, what goes to space should stay in space. Of course, that's going to be a lot more expensive for the space development people at this point right now, because to take some things, what that means is creating a junkyard orbit or a graveyard orbit in middle Earth orbit or somewhere where it is safe to take this stuff so future generations can use it for their benefit. And the only, of course, that would mean policy changes that and the expenses, and people just won't do that at right this point because of the nature of space development and the investment involved in it. But to me, if it is done, monetizing space debris would be the benefit and cause it to, because by burning it up in the atmosphere, all you're doing is burning up cash. That could have value in the future. Some of these objects are very big and could be repurposed in the future. So I just want to see on the financial end of this, if we do go to that level where we phase out reorbit or reentry as a space debris mitigation strategy and build a resource orbit. Is that something that you see potentially as a factor that could help it, as well as it's going to cost a lot more, but it would really bring about space development? We would need tugs, tethers, all kinds of things to make that space debris not fall into the atmosphere, but go to a resource orbit. So it's more of a general discussion on that, but I think it needs to be opened up. Monetizing space debris is really the only way to do it. Thank you for my rant.
Thank you very much for your point, and I think you laid down the problem and opportunity in a way that I wouldn't be able to do it so gracefully and as gracefully as you did. That's spot on. This opens doors for the in-orbit circular economy, where we could for sure, and I think that's the only way to be able to sustainably access other celestial bodies, is to be able to repurpose, refurbish, even recycle, and assemble spacecraft and launch vehicles in orbit to go to other celestial bodies. And there is definitely a huge financial opportunity there, because as you mentioned, this hardware takes a lot of time and money to develop, and it's just a waste to burn it up in the atmosphere upon reentry. However, on the other side, we need to ensure that space keeps sustainable, keeps being sustainable and open for access, which means that we need to remove the objects that are derelicts in orbit. The only solution is logically doing so while in orbit. So that's spot on. The question being whether we are already there in terms of technology readiness. That's a question that I would say would go beyond my expertise, although I have, of course, my own opinion. But I'm a strong believer that in the next decade we will see this being a reality. We have a couple of initiatives privately held that are already developing this sort of initiative, such as fuel stations in orbit, doing actually having forgeries for recycling in orbit. The current advancements in close proximity operations and rendezvous are enablers for this kind of solutions. So I think we're getting there progressively, and I see it as the option to move forward for sure. Thank you for your comment. Let me perhaps go here with perhaps a follow-up question in person, and then I'll go back online.
Yeah, I was just wondering if this shift towards sustainability and reusability of spacecrafts would perhaps increase the likelihood of some kind of mass breakup or Kessler syndrome effect in space, and if it would also potentially decrease access to higher orbits because of the massive amounts of stuff that we would have to put into graveyard orbits.
Let me ask you, where would you put the graveyard orbit? Higher than the low Earth orbit?
I would put it higher than low Earth orbit. Otherwise, it would just probably burn up in the atmosphere anyway.
But in that case, it would prevent the access to
Like geo.
the geo, right? Yeah.
Yeah, that's a very good point. I would say that the goal of a graveyard orbit would be for it to then be our playground to recycle and to repurpose those objects. Of course, that having a graveyard orbit would constitute yet another barrier and another potential risk for collision in between objects that are uncontrolled. That's for sure a concern. I believe that the point of the previous comment was having a graveyard orbit so that it's easier to access these resources, and then hopefully being able to repurpose them to other initiatives. And also another important point is that increasing the altitude of a satellite or of an object in orbit is most likely more expensive than just letting them burn, letting them come down. And that's not only a financial and an economic point of view, but also from the mass budget of your spacecraft. If you need to increase the orbit at the end of life, then you need to increase the mass of propellant in your spacecraft, which means that it's more expensive to launch, and so forth. So this is not an easy equation to solve. It's definitely a problem with tons of trade-offs that we need to look into in further detail. Yes, online.
Yeah, I have a question. I want to thank you also for such a informative presentation. It was very enjoyable. I understand that at sufficient altitudes, quite an amount of oxygen is found as an atomic species rather than as a diatomic species, and so I'm curious how this might possibly have effect on the chemistry of objects re-entering, whether that has any impact into the actual compounds that are formed during exposure to atomic oxygen. And then I have a comment regarding the storage of objects in space, and I'm sure everyone has heard of and is aware of the Kessler syndrome, and so that would be a problem perhaps if you have sufficient objects for storage in some type of orbit, regardless of whether they'll be utilized in the future or not. And I guess there's enough problems with space debris at the moment that's already maybe a considerable impact on orbiting functional satellites. But thank you for the presentation.
Thank you for your question. Well, I'll start with your second point by agreeing that's something that would need to be equated in the decision of moving a derelict to a higher orbit or just doing the whole refurbishment or repurposing in situ. That's part. I would say that it's part of the trade-offs that I was mentioning earlier. As for the first part of your question, atomic oxygen versus molecular, that's a function of altitude and also re-entry speed. And you are correct in your comment that atomic oxygen gets more prevailing, but this happens for higher altitudes, especially above 100 kilometers. For lower altitudes, the molecular oxygen species has 2 or 3 orders of magnitude higher number density than atomic oxygen, and that's the reason why we didn't include it in this first take of the molecular dynamic simulations. But your point is well taken. It's just a matter of comparing the magnitude of the number density of both atomic and molecular oxygen at different altitudes, and we tried to simplify by not including the atomic oxygen because there were 3 or 4 orders of magnitude difference between a molecular and atomic, and molecular was prevailing at that altitude.
Jose, really quick, Dave is asking if you could put your references slide back up, please.
Of course.
Thank you.
I'll take a question here from in person.
much. Can you ask the question and I'll just repeat it?
Sure. Less of a question, more of a, I guess, general discussion / questions. First one. Had like two general discussion / questions. Also, thank you for your presentation. Very, very informative. The first one was, it seems like the research focus on your side was the how much of the satellite is decomposed into the aluminum oxide and the bare oxide, and how much of the percentage of that satellite is burned up in the atmosphere re-entry versus what's deposited as materials on the ground. I also think that the focus or more so interest in the industry would be with the resulting effects of that, meaning instead of, because the in situ measurements for how much is deposited from that spacecraft is quite difficult to measure, a conservative approach can be taken such that we assume, let's say 50% or 30% or 20% of that satellite or rocket body is then decomposed into the atmosphere, and then the resulting effects on the atmosphere from that conservative estimate. What would you say that the effects are when that happens, in terms of the ratio of that satellite for the ratio of all the satellites for the next few, like the next decade or so? If we were to assume different burn percentages for each satellite, would this be a negative effect overall, positive? But as you mentioned, it's quite difficult to assess that. But is there research in this area being done as to the posterior effect of the percentage being burned? And that's my first question.
You want to ask?
Yeah, and then my second question, and I can repeat. The focus on the aluminum being, the reason aluminum is used in spacecraft development right now is because of the launch vehicle vibrations, to be able to sustain the vibrational loads from the launch vehicle. However, once for most satellites currently in orbit, the material, the actual physical structure and the stiffness requirements and whatnot is less of an importance once it's in orbit. So let's say, for example, we are able to make our satellite designs better in terms of making the electronics, hardware more vibration hardened for launch. We can shift the focus from changing the material structures from, let's say, aluminum 6061 or 7075 T6, which is the standard for most small satellites right now in LEO, to a different material. Is there any recommendations as to what would be more sustainable? And there are many different types of materials that can be used. I know there's a university in Tokyo that is looking into wooden satellites, so wooden satellite structures, but that's for like very small satellites. So maybe the emphasis can also be on what material shifts can be made from the spacecraft side to make it more sustainable in terms of launches. Maybe I have a comment on those two things. Thank you.
Thank you. I'm going to answer from here because you may want to comment in and rebate in some way. Okay, your first point concerning the mass fraction that we consider for satellites, right? Or the mass fraction that we consider to be injected versus the one that reaches the ground. I'm not aware of any study that used that as that had done any sort of parametric study with regards to this. Of course, we can tune this knob and see if it actually matters and changes anything. My gut feeling would be that if we change from 95 to 85 or 70%, and for sure, let me just give you a side note here. For sure, it depends on the mass of the satellite. If we're referring to a larger spacecraft, it will probably some of it will make it to the ground. And therefore, we would not consider 95%, we'll probably consider 65. That's why I gave a range. If we're speaking about a small satellite, like a node of a mega-constellation, I would be surprised if the number would be below 95%, and because most of them are designed for demise, which was a trend from the last couple of years, which again, from a risk assessment standpoint, makes total sense. Design spacecraft and launch vehicles for full demise in the atmosphere so that they don't get to the ground. Point here being whether there is an unintended consequence that we didn't foresee because we couldn't due to the increased re-entry rates. answering your first question, I think tuning the knob from 95 to 70%, that's a 15% difference when we are increasing the mass of that re-enters in this proportion. I would be happy to see a study. I would be surprised if the results change that much, but I think that's something that should be assessed once we have a clearer idea of how the microphysics in the mesosphere work, because that would tell us a lot about something that I've been thinking, which is the atmospheric carrying capacity. What's the concentration of these species that the atmosphere can deal with before we trigger some sort of negative impact. That's a question that will come, I believe, only after we solve the physics questions in the mesosphere. To your second point, with regards to what other alternatives, that's a very good question. So my point with carbon-based alternatives, being it CFRPs, carbon fibers, or other carbon alternatives such as the wooden satellite, is that, well, black carbon is not that much. We are concerned with carbon in the atmosphere already, and I think there is a reference that points that black carbon is 500 times more potent when high up in the mesosphere. I can get you this reference. The only question mark here is whether black carbon is formed during re-entry of a wooden satellite or a CFRP structure. The answer to that is I don't know. And if someone in the audience or online can say something about this, that would be great. But even if black carbon is not formed, we have other potential chemical reactions in the carbon chain that could happen, such as the such as monoxides and dioxides, right? So I would say that without a very concrete assessment of these alternatives, we wouldn't be able to say that this is preferable when compared to aluminum. And I think this also clearly points us to the initial argument that the solution is circular economy in orbit, recycling and repurposing, instead of having things burning up in the atmosphere. Although I agree that the short-term solution would need to pass by a more responsible and sustainable attitude and approach towards this phenomenon, because most likely we won't have recycling options available from the technical standpoint in the next couple of years. So yeah, but those are two good points, and thank you for that. You want to follow up with?
Yeah, sure. No, I really like those answers. Thank you so much. Yeah, it's a very good point. I did not consider that alternative is essentially on paper more sustainable options, such as like you said, carbon or carbon-based materials could actually be more harmful than the aluminum structures that we're building today. There's going to be a lot of technological advancements needed to do any type of in-space servicing, refueling, especially the fact that as technology improves over time, we want to have new and more advanced satellites that are being launched, and you might not necessarily want to operate those LEO satellites with the older technologies, as well as the fact that there's always radiation damage that's happening over the span of a 5 to 10 year cycle of a satellite. So it's quite a difficult challenge to address, and I think we're never going to get away from LEO satellites being deposited or burned up in the atmosphere as a form of disposing of the satellite, just because LEO is very difficult to, the delta V required to escape that orbit is quite high, and there's no such like graveyard orbit potentially possible for the fact that small satellites are built with low mass budgets and therefore low delta V capabilities. It's quite possible, and that's what they do in GEO and NEO. But LEO is a very hard challenge to deal with. So dealing with the disposing of the satellites in the lower atmosphere and the mesosphere is probably something we should definitely focus our research on, both in terms of the effects of the satellite being burned up, like how much percentage as your research is doing, as well as the overall effects of that and how we can make that better and more sustainable. But yeah, thank you.
I will perhaps now give the floor online in case someone has any question.
Yeah, I have one comment actually in regards to alternative materials for satellites. There was a satellite last year, Lignosat, I believe was the name of it, that was made of wood, and apparently structurally it seemed to perform quite adequately, if I understand correctly. I have one question, which is more of a theoretical question. Have any studies been done of the reentry atmospheric characteristics in atmospheres other than Earth's containing oxygen? For example, say reentry into a Mars atmosphere that's mostly carbon dioxide, and it's just out of curiosity whether that has even been looked at.
Just to clarify your question, you're referring to the point of fluid structure interactions. How does the material ablate upon reentry in other planetary atmospheres?
Well, and whatever chemistry might occur in that case, obviously without any significant amount of oxygen, what would happen? Would aluminum just material just rain down as molten microdroplets? I was just curious. It's kind of an esoteric thought, but perhaps in the future, if Mars is colonized, reentry of objects into the Martian atmosphere might be of some consequence. It was just a thought, but that was the general direction of my question.
Well, just commenting your point, I am not aware of research done with the aluminum specifically in other planetary atmospheres. Of course, you're probably also aware of research done with heat shield materials, because that's very much needed to decelerate when landing in Mars. But that's a completely different material or composite to look into. So with respect to aluminum in other planetary bodies, I am not aware of research done. Any other questions from the online folks?
Yeah, I have a question that I put in the Q&A. An interim solution that might be helpful could be refueling some of those 5-year life satellites. They seem to be limited mostly by the mass fraction of propellant. Nowadays, it seems to be mostly argon that they can retain, and they're all deployed in rings, which would make it possible to build a refueling satellite that would slide around that ring from satellite to satellite with very low energy cost, very low delta V, and refuel them. If you could refuel them twice so they lasted 15 years, then you'd reduce the demise by a factor of 3. And this might be a lot simpler and accessible sooner than the possibility of trying to disassemble all those satellites in orbit and reuse their component materials. So I wanted to raise that as an interim possibility. Thanks.
Yeah, and that I believe has been proven in GEO with the mission extension vehicles a couple of years ago already. And I'm aware that a couple of other private initiatives are trying to do so in low Earth orbit. But the question will always be standardization. How do we make sure that our fuel pump is able to match the so yeah, I totally agree that this is something that could help us moving past the delta V problem. Just question being when will this be ready to deployment? I totally agree. Thank you for your comment. I'm probably going to give the floor to some folks here in person in case there are any further questions. Yeah. Okay. This is the only two. Okay.
I'm not sure how long the cord is. Oh, perfect. So first off, excellent presentation. I didn't get a chance to say that, but yeah, excellent presentation. You may have talked about this earlier. Has there been any research into how quickly satellites or spacecraft burn up based on the size? Like if you disassembled one in orbit, would it burn up faster, slower? Because I'm kind of looking at where can you place the debris in the atmosphere?
That's a very good point. Thanks for your question. So So to answer your question directly, I haven't seen a parametric study about how fast it re-enters when compared to the mass, but I think we can fairly easily and quickly measure it, as it is a function of the mass. I mean, it will hit hub. You'll be able to figure it out what's the temperature now and how fast this temperature would increase as a function of mass. And usually also as a function of the angle at which the reentry takes place and so forth. We have ways of estimating this so as to maximize heat load or to minimize heat load or maximize or minimize heat soak, which means are we aiming for a higher temperature for a longer period or a higher temperature for a shorter period or a lower temperature for a longer period. And this is also how heat shields are designed. Essentially, we try to make sure that we can withstand that maximum temperature, but for a lower period of time. So this is, I mean, to answer your question, that would be a very interesting approach to look into. The only point I would like to raise is that the mass we would be injecting in the atmosphere would be the same, right? So the different altitudes. So it would be a function of what would be how susceptible to the oxygen concentration at those altitudes these objects would be, and that's a very interesting point. So disassembling the spacecraft in orbit so that we have some sort of differential ablation at different altitudes, and that would be able to contribute differently.
Well, you just make the screws out of plastic or something.
Right.
Then they melt first.
Right. That's a very interesting point. Not aware of any trade-off study done in that capacity. But yeah, thank you for your comment. I don't know if you want to rebate or follow up.
No, that was it. Thank you.
Thank you. Any other question from here in person? Yeah. Okay.
Thank you very much for the presentation. It's very good. I'm curious if you're aware of any active hardware-based experiments that are ongoing or being planned to clear up some of these questions.
I'm assuming on the physics side, clear up these questions on the physics side, right?
Yeah.
I am aware.
Or chemistry.
Or chemistry, yes. I would say that, so there is an upcoming mission from the European Space Agency called Draco. They are trying to further understand how spacecraft break up at these altitudes with in situ measurements. So this is, to my understanding, set to be some sort of formation flying, which is very similar to what was done in the past with the REBR, the re-entry breakup recorder, where we had this small aeroshell within the spacecraft that recorded data. I think it was mostly inertial data a couple of years ago. To my understanding, this mission is along the same lines, but also trying to get past the data that was gathered from the REBR. Other than that, I wouldn't be surprised if these initiatives from NOAA would kept on ongoing with further measurements in the stratosphere to further understand if these first observations are replicated in other locations and so forth. Other than that, and other than what it's publicly aware, I'm not aware of any broad effort to unveil these mysteries in the mesosphere, because as I was mentioning, this is not easy to solve, and also it's going to be cost intensive as well. I don't know if I answered your question or if it was too limited.
You did. Thank you. Perhaps we should have a discussion afterward. Sure. Thanks.
Any other questions from folks here in person? Okay. Anything else online?
Yeah, there was a question from Goldie here that I don't want to miss. Let's see. So it reads, great work and presentation. Can you please summarize where you see conservatism in your assumptions with respect to masses, amount demised, and ratios of materials?
Thank you, Goldie, for the question. So I'm interpreting that conservatism's, where do I see that my approach was conservative with respect to the assumptions I made. And this will be a non-extensive list because I'm doing it on the fly right now. I was conservative in the altitude. I'm assuming basically the top of the mesosphere altitude, which means that the number density of oxygen is the lowest I could consider. At lower altitudes, the amount of oxygen would increase, and therefore I would expect the oxidation yield to also increase. We can also list as a limitation the fact of not including other air species in the mix, such as nitrogen, and also not including other chemicals in the molecular dynamics model, such as the other constituents from aluminum alloys. Although I would not expect that to change much the results given the high reactivity between aluminum and oxygen. Even if we take, for example, into account the treatments that aluminum alloys are subjected to, I would be surprised if that would change the results extensively. And these are perhaps the two main points. And of course, that if we then consider atmospheric models and settling time and condensation rates, there's a huge limitation due to the lack of publicly available, lack of data in the mesosphere to back these assumptions in atmospheric models. I think that's pretty much it. But happy to discuss further the limitations if you're interested, or if you want to follow up with the question. Thank you.
I have a question. In the approximate time frame of the 2030s, NASA is planning on reentry disposal of the ISS, and I assume this will probably be about the largest man-made object to undergo atmospheric reentry. So I'm just curious, are you aware of any possible studies that are planned in order to observe and analyze the reentry profile and composition of atmospheric deposition that it might have? Just curious if that's something that might be planned for that particular reentry of the ISS.
Well, I really hope that that we are going to use that chance to measure it thoroughly. I think it's probably going to be the most visible re-entry ever made, and therefore the biggest opportunity to further understand this phenomenon. But your question was if I am aware of any current initiatives, and the answer is, of course, that I may have missed something, but I'm not aware of any current initiative aiming at that. We still have some time to prep it up, and perhaps to learn from more short-term initiatives to measure re-entry events. I wouldn't be surprised that comes to be. But answering your question directly, I am unaware of any current initiative to measure it. But I'm very hopeful that it will take place. It's a huge opportunity.
I would hope that they'll end up saving the ISS, or somebody will buy it for space debris. That's actually really very upsetting that they're going to go that route to burn that up, when we have the potential to use that as a place where we could bring it to a higher orbit. There's enough money to make that happen, I think, rather than spending, as some people know, SpaceX has been given the contract to actually deorbit the ISS, or at least to study how to deorbit the ISS. It should be, it should be studying how to keep it in space for other uses. Thank you.
I agree.
While I have the mic, I do have one other question. Do you know of any studies in China or in India and Russia, some of the other space development countries, on their research on this, or what their practices or thoughts are within this in this paradigm?
As for ongoing studies on this phenomenon, I'm not aware of any recent studies carried out from researchers on those locations. As for general practices, to my awareness, it comes down to national law. So the common practices being in the US and in Europe to aim for from a casualty probability risk under 10 to the -4, under 1 in 1,000. So we need to prove that when the satellite re-enters, when an object re-enters from orbit, that the probability of casualty on the ground is less than 1 in 10,000. I know that this is translated into national law, although I'm not an expert in this field, and I would not claim if this is also applied or deployed in the countries you mentioned. If there is someone in the audience that could chime in and is an expert on this, I would appreciate. I know that this is the practice in Europe and in the US, but I would defer to someone with the more expert in the subject to comment about other countries.
Thank you. I actually think you're the lead researcher on this subject. You're way out in front.
Thank you. Alrighty. Any further questions, either online or here, folks in person? So I would give the floor back to Ken or Louise if you want to make some final
Thanks
comment.
again for all your great effort on this. Really appreciate it.
No, thank you. Appreciate you.
Yeah. Thank you, Jose. If no one has any further questions, I want to just talk about two things before we break here. First one, like Ken said at the beginning, the student mini conference that we have coming up on February 21st. If you're interested in attending, please send either Ken or I an email. Right now, we do have it, specifically catered towards students, but we're going to open it up to the public if interest is there. Again, this conference is just a day for the students within our organization, within the LA chapter, to kind of showcase what they've been working on throughout the past year. Always very informative. We have a lot of fun. But yeah, the president of AIAA is going to be there. Just an FYI. So again, if you're interested, please let Ken or I know. And then secondly, Jose, thank you so much for presenting. It was well worth the wait. And also, I'd like to formally invite you to our awards dinner on May 14th. This is a day that we recognize, outstanding people within our chapter, within the organization. And we'd like to invite you to be recognized at this event. So we can talk details later, logistics and all that, but we're very, very excited that you're here with us and presenting.
Thank you.
So thank you, Jose, and thank you everyone for showing up. I hope you all enjoyed today. I think that's it.
All right, guys. Thank you. Have a good one.
Thank you, Jose.